This video is about the order of an element of a group. Our goals for this video are to state the definition of the order of an element in a group, to prove some basic properties of orders of elements, and to work several examples and concept checks. For this video, you should be familiar with these concepts. The cyclic group generated by an element, along with the notation, the cyclic group generated by the element A is denoted in brackets, and this consists of all of the powers of A. Using the operation of the group G. Our examples will be drawn from the integers modulo n, from matrices, and from roots of unity. We will use the following notational conventions. Z will stand for the set of integers. For an integer n greater than or equal to 2, Zn will denote the group under addition of integers modulo n. K star will be the group under multiplication of invertible elements of K, where K could be the rationals, the real numbers, the complex numbers, or Zn. Mn of K will denote the group of all n by n matrices with entries in K. And gln of K will be the group of all n by n invertible matrices with entries in K. Okay, so let's start with our main definition. Let G be a group with identity element E, and let X be an element of G. The order of the element X is the smallest positive integer n, if it exists, such that x to the n equals e. And we will use this notation that looks like absolute value to denote the order of x. If the group has addition as its operation, and we use additive notation, then the definition looks like this. G is a group with identity element, generally called 0. Then for an element x in G, the order of x is the smallest positive integer n, if it exists, such that nx equals 0. That is, the smallest number of times that we have to add x to itself to get the identity element. If there is no such n, then x is said to be of infinite order. So just a few examples. The identity element of a group always has order 1, since e to the 1 is always e. So in particular, for the group of integers under addition, the identity element is 0, so the order of 0 is 1. On the other hand, the element 1 in Z has infinite order, because we can add 1 to itself any number of times, and we will never get 0. R star is a group under multiplication. This is the group of non-zero real numbers. The element -1 has order 2, since -1 to the 1 is certainly not equal to 1, but -1 to the 2 is equal to 1, which is the identity element of R star. In Z15, this is a group under addition. The class of 7 has order 15, because if we keep adding 7, the smallest number of times that we have to add 7 to itself to get 0 is 15. On the other hand, in Z15 star, which is a group under multiplication, the class of 7 has order 4, since certainly 7 to the 1 is not equal to the class of 1. The class of 7 squared is the class of 49, which is the class of 4. which is not 1. The class of 7 cubed, which is 7 squared times 7. So that's the class of 28, which is the class of 13. It's also the class of -2. And finally, 7 to the 4 is 7 cubed times 7. So that's the class of -14, which is the class of 1. Since 4 is the smallest power that we can take the class of 7 to get the class of 1, the order of the class of 7 in C15 star is 4. Now you might observe that the word order in abstract algebra is used in two very different seeming ways. The order of a group G is the number of elements of G if this number is finite, and otherwise we say G has infinite order. Compare that with our new definition that the order of an element of the group G is the smallest positive integer n, if it exists, that we can raise that element to get E. And otherwise we say X has infinite order. So why would we use this same word, order, for two seemingly very different things? Well, it turns out that these concepts are closely related. And that brings us to our first fact. Let G be a group, and let A be an element of G. The order of A is equal to the order of the cyclic group generated by A. So that sentence uses the word order in both senses. The order of an element is equal to the order of a certain group. So that is, the order of the element A is equal to the order of the cyclic group generated by A. All right, so let's sketch a proof of this. First of all, the element A might be of infinite order. In that case, we claim that A to the I is not equal to A to the J for all I not equal to J. If A to the I is equal to A to the J for some I and J, without loss of generality, we could suppose that I is less than or equal to J. Then if we multiply both sides by A to the -I, we will get A to the J minus I equals A to the 0, which is E. But since A is not of finite order, we must have J minus I equaling 0, because we've raised A to the J minus I and gotten E. Thus, I must be equal to J. And therefore, there are infinitely many distinct elements in the cyclic group generated by A. For case 2, suppose A is of finite order. Let's call that order n. We claim that the elements E, A squared, and so on up to A to the n minus 1 are all distinct. First of all, A to the k cannot be E for every k from 1 up to, not including n, by definition of n. Because remember that the order of A is the smallest positive integer that we can raise A to get E. So we certainly cannot raise A to any smaller power than n to get E. Now, what if there is a repetition in the middle of this list? If A to the I is equal to A to the J for some I and J between 1 and n minus 1, without loss of generality I being less than J, then A to the J minus I would be equal to A to the 0 would be E. But J minus I is a positive integer strictly less than n, which would contradict n being the smallest positive power of a that equals e. Therefore, our list has no repetitions. To see that this list actually constitutes all of the elements of the cyclic group generated by A, it remains to show that there are no other powers of A that are distinct from these on the list. And for this, we can note that if m is any integer, we can use the division theorem to write m equals nq plus r for some q and r where r is non-negative and less than n. And therefore, a to the m equals a to the nq plus r, which is a to the n all to the q times a to the r, which is equal to a to the r, since we know that a to the n is the identity element. Therefore, a to the m is already one of the elements on this list. Thus, the cyclic group generated by A consists precisely of these n elements, and therefore has order n. Here we come to our first concept check. Let A be the matrix 2, 1, 1, 1. Part A, find the order of A, assuming that A is an element of GL2 of Z3. Part B, find the order of A in M2 Z3. Here you should pause the video and try to work the answer out for yourself as much as you can before going on. Okay, so here's our solution. For part A, we are thinking of the matrix A as being an element of GL2 of Z3, which is a group under multiplication of matrices. So we're going to multiply A by itself as many times as we need to in order to get the identity element of GL2 of Z3, which is the identity matrix 1, 0, 0, 1. And you can see that A squared is 2, 0, 0, 2. That's not the identity. A cubed is 1, 2, 2, 2, which is not the identity. And A to the 4 is the identity matrix. So therefore, the order of the matrix A is equal to 4 in GL2 of Z3. For part B, we are working in M2 of Z3, which is a group under addition of matrices. So we have to add A to itself as many times as we need to in order to get the identity element of M2 Z3, which is the 0 matrix. When we take 2 times A, which is just A plus A, we get 1, 2, 2, 2. Observe that the entries are classes in C3. So 2 plus 2 in the first entry is 4, which is congruent to 1 mod 3. And 1 plus 1, of course, is 2. 3A is A plus A plus A. And when you work that out, you do get 0, 0, 0, 0. Therefore, the order of A is 3 in M2Z3. Next, if A is an element of a group G that has order n, then certainly A to the n equals E, but the converse does not hold in general. For example, in Z10 star, we can observe that the class of 9, when taken to the 4th power, is the class of 1, which is the identity element of Z10 star. But the order of the class of 9 is not 4. In fact, the order of the class of 9 is 2, because the class of 9 squared is also the class of 1. However, the following is true, and this is our second main fact. If A is an element of a group G, and A to the n equals E, then the order of A divides n. In our example, we saw that the class of 9 to the 4th power is 1. The actual order of the class of 9 is 2, which is a divisor of 4. Proof: let k be the order of A, and suppose A to the n is equal to E. Again, we can use the division theorem to write n equals kq plus r, where r is non-negative and less than k. Since k is the order of A, we know that A to the k equals E. So we can write E equals A to the n, which equals A to the kq plus r, which is equal to A to the k all to the q times A to the r, which is A to the r. But k, by definition of the order of A, is the smallest positive integer such that A to the k equals E. And r is non-negative and strictly less than k. Therefore, to avoid a contradiction, we must have r equals 0. Therefore, n equals kq. And therefore, k divides n as desired. Here's our second concept check. In Z20, we can note that 10 times the class of 8 is the class of 0. Use this information to find the order of the class of 8 in Z20. So pause the video and come back when you have an answer. Okay, so by fact 2, we know that the order of the class of 8 is a divisor of 10 because we were able to add the class of 8 to itself 10 times to get the class of 0. Thus, we only need to check 1, 2, and 5 as possible orders of the class of 8. Well, certainly the order of the class of 8 is not 1 because the class of 8 is not the class of 0 in Z20. 2 times the class of 8 is the class of 16, which is not the class of 0. But 5 times the class of 8 is the class of 40, which is the class of 0. Thus, the order of the class of 8 in Z20 is 5. We don't have to check 3 or 4 as possible orders of the class of 8, because 3 and 4 do not divide 10. One more concept check. Let S1 denote the unit circle in the complex plane. As an exercise, you should convince yourself that S1 is a group under multiplication. Now let U be an nth root of unity. Prove that the order of U in S1 divides n. And part B, prove that the order of U equals n if and only if U is a primitive nth root of unity. So pause the video and come back when you're ready. Okay, so for part A, this should be very easy if you understand the definitions. Since U is an nth root of unity, we have U to the n equals 1. So by fact 2, the order of U divides n. And for part B, we have that the order of U is equal to n if and only if n is the smallest positive power of U that equals 1, which in turn is the definition of being a primitive nth root of unity. So in summary, The order of an element A in a group G is the smallest positive integer n such that a to the n equals e, or na equals 0 if you are working with additive notation. If no such n exists, A is said to be of infinite order. And we had fact 1, which is that the order of A is equal to the order of the cyclic group generated by A. And fact 2 says that if A to the n equals E, then the order of A divides n. As a question for further thought, can you think of an infinite group with exactly 2 elements of finite order? Can you think of an infinite group with exactly 3 elements of finite order? I hope you found this video helpful.